All right, welcome back, everybody. Welcome to chapter two. Today we're entering chapter two, which is all about functions. And the first section is actually just all about functions in general. So let me pull up the slides and we will get started. Here we go. All right. So just a quick chapter overview. The first section is just about functions. We're going to set up what a function is, talk about some just function notation, that kind of thing, build some intuition for functions. That's the section we're doing today. The next section, 2.2, is all about the graph of a function. We'll talk about how you can graph these things, talk about the vertical line test. Maybe you heard of that before. Chapter or section 2.3 is all about graphing transformations of not only functions but also relations as well, like shifting things around, scaling them, rotating them, that kind of stuff. Section 2.4 is all about important attributes of functions. Many functions have certain attributes that we want to look out for, like evenness or oddness. We can talk about local minima, local maxima, that kind of thing. Section 2.5 is a critical section. That one's all about compositions of functions. And basically, that discusses taking functions and putting one inside of the other, which is something that we do a lot in math and science, nesting functions, daisy chaining functions together. And then the last section is section 2.6, and that's all about inverse functions, which basically undo what the forward function does. So we'll get there by the end, by section 2.6. So, as far as section 2.1, what we're going to do today, we're going to go over the definition of a function, get some motivation for why we care about these things. We're going to build some intuition for functions. We're going to talk about function notation, which is critical to get comfortable with. So we'll spend some time on that. We're going to talk about the domain, range, and codomain of a function. We'll go over the four representations of a function. We're going to go over some notation for domain and range. And to do that, we need to do a little sidestep and talk about unions and complements of sets. So we'll talk about a little bit of set theory in this section. Then at the end, we're going to talk about domain and range and just how we can interpret these things in respect to, or with respect to inputs versus outputs. All right. So we got a lot of stuff, but we'll be able to cover it all. Shouldn't take as long as like the last recording, the last lecture. So let's get started here. So what is a function? The definition is the important thing to start with. So a function f is a rule. It's a rule that assigns to each element x in a set D sub f called the domain. It assigns exactly one element, f of x, in a set R sub f called the range. All right. So this is a moment where I want you to just think about this for a second. Look at this definition, read it out loud in your head, or read it in your head for a minute. Okay. And now I want you to say it out loud. I just want you to read this out loud. Remember, you don't need to read it to anybody, but if you're watching this with somebody, turn to that person and read this definition out loud to them. Have them read it out loud to you, just to give your brain that verbal feedback. Right. Okay, now there's a few things that I need to emphasize here. So for one, a function is a rule. It's basically a process. It's something that tells you what you want to do to stuff, right? And for what it does is it takes an element in its domain and it assigns an element f of x in the range. So pictorially, you can really think of a function using this picture. You've got a set, which I'm picturing with this oval, right? This is the domain. This is a set over here. This is the range. And f is the arrow that takes you from the domain to the range. All right. So f quite literally is this arrow in this case. So it takes x and it maps it over here to f of x. That is what a function does. Okay. Now, some things that I need to emphasize again, or emphasize for one, the concept of a function is probably the most important mathematical concept you will learn. You've really got to get comfortable with it if you want to do math and science. It is not as difficult to get comfortable with as you may think. We are here to help you make sense of it, but you're going to use them forevermore, forevermore. The other important thing is notice that the definition we were just looking at It's extremely general. It doesn't involve numbers at all. Let's go back. Here, let's read it again. A function f is a rule that assigns to each element x in a set D sub f exactly one element f of x in a set R sub f. There's no mention of numbers whatsoever. You notice that? This isn't talking about real numbers or complex numbers or points or anything like that. The concept of a function is extremely general and very abstract, and it's good. We want it to be that way because the functions that you work with, many of you, they're not going to be numerical functions where you're putting in a number and getting out a number. Even, for example, when we were looking at Mathematica, in the previous section, or yeah, in section 1.6, those were functions, but they weren't numerical functions. These were functions where we were putting in all sorts of stuff. We were putting in algebraic expressions. We were putting in equations. We were putting in inequalities. Those are functions. So you really do want to think about functions in a very general way. So there's that. Now, here is the thing. Numbers are easy to play with. So a lot of times we use numbers to gain intuition about functions in these types of courses. But as we do, I really do want you to let your mind wander and wonder about the possibilities that are afforded by this generality, the generality in this definition. Um, maybe more relevant here. In Calc 1 and Calc 2, you're going to spend a lot of time studying two really, really important functions, the differentiation operator, which looks like this, and the integration operator, which looks like this. So if you've seen these types of symbols before, they're functions, and they are rules telling you what to do to the things that you put inside of them. All right? So maybe for a little intuition, you can think of a function like a box, and that box transforms objects into new objects based on some rule that we often label f for function, because it's a good label to put on the box. The only requirement of a function here is that only a single object can come out of the box at a time, and we call that box. I'm sorry, we call that thing f of x. So what I'm saying is this: if you put an object into this box and it spits out two different objects as a result, that is not a function. Okay, that is not a function. A function, you put one thing in, you get one thing out. You can't put one thing in and get a whole bunch of things out. All right. But quite literally, you can think about it like this. So the way that I like to think of it is X, you take X and you drop it into the box. The box is called F, and F does something to the inputs that you put into it. And then what comes out of the box is F of X, right? So X goes in, it gets F'd up, and what comes out is F of X. All right? That is what a function does. Okay, now we got to talk about the notation, and this notation is absolutely critical. In my experience, the only reason that students struggle with functions is because they're not making sense of this notation well enough. So we're going to look at the anatomy of this notation very carefully right now, right? This is the symbol that we're looking at. So when you see this symbol, it is pronounced f of x, okay? And what does each one of these little pieces mean? Well, the symbol that is inside these parentheses, that represents the input. The symbol doesn't matter. You can use whatever symbol you want, X, T, A, B, smiley face, cat emoji, whatever you want to use, whatever is going in between those parentheses, that is the input, the thing going into the box, okay? Then what does this represent? This letter or symbol or whatever you want it to be represents the rule or the name of the function. That thing or this symbol is representing the process that you are going to perform to the input. All right. And now here is the big takeaway. So take this to heart. Remember this very well. The whole symbol itself represents the output of the function, okay? So when you see f of x, it is the output of the function. It is not the function itself. There's a distinction between the function itself and the output that it spits out. This is the function. This is the thing that comes out of the box, okay? Big difference. Right. Um, yeah, I've said this already. Remember that when you see this symbol, f of x, it should be treated as a single object algebraically. So don't try to factor out f or like pull f off of this. That doesn't make any sense, okay? This represents the output of f, okay? So you can't like detach f from the x in this case. Um, so yeah, this notation is also really well designed. You may not think so, but it is really, really well designed because it explicitly indicates the input, it explicitly indicates the output, and it explicitly indicates the rule all at once. So it eliminates any ambiguity that we might have about what is going in and what is coming out of that box. Okay, that's why it's really nice notation. Um, uh, Oh yeah, the other thing is this. There are things that are not just functions. So a relation between quantities, it could describe a function of one variable in terms of another, but this is not always the case. And the function notation addresses this. So when you write something like y equals f of x, what we're saying is y is, right, is a function of x. Y is a function of x. And so what that means is if you're given any x, there's a single corresponding y value, right? That's what a function is, right? Now, some equations represent functions and others do not. So for example, y could be a function of x, but x may not be a function of y. That's why it's really important to distinguish what is going in and what is coming out, because it's like, what's going on, right? That's why this is nice notation. It's very clear. X goes in, f is what happens to x, and f of x is what comes out. So not every equation and not every relation describes a function. So for example, this is the equation of the unit circle. Look at it now, memorize it. Here, I'll throw the thinker up real quick. We're going to see it, man, hundreds, maybe thousands, well, hundreds of times at least. We're going to see this equation. It is the equation of the unit circle. So pictorially, this equation represents a circle centered at the origin with radius 1. Okay, that's what this equation is representing geometrically, right? Remember algebra, geometry, BFFAE. So this equation, it actually doesn't describe y as a function of x, nor does it describe x as a function of y. And we're going to see this in the activity related to this section. Oop, let me do that. There you go. We're going to see that in the activity related to this section. It's okay if that doesn't make sense right now, but you'll see it when we work together on it, okay? The point is, not every equation represents a function, so beware. Let's look at some examples and build some intuition. How about this? This is a nice, simple algebraic function. F of x is equal to 3x plus 1. Let's break it down into the pieces. Okay, x is the input. Makes sense, right? F is the rule given by this sentence. The rule is multiply by 3 and then add 1. Okay, so when you see that letter F, I want you to think of it as this sentence. And what that does is whatever you put into that box, it multiplies it by 3 and then adds 1. That is F, okay? Then 3x plus 1, which is equal to f of x, that's the output of the function. That's what results after you put x into it, multiply by 3, and then add 1. That's the output. So this picture, it's very, very literal, right? X goes into the box. What does this box do? It takes whatever comes into the box, multiplies it by 3, and then adds 1. What comes out of the box? 3x plus 1 for whatever x is in the domain of this function, right? Got it? Okay, let's do a specific x value. So think about this one. Let's do f of 4. So here 4 is the input. So we're dropping 4 into the box. It goes right there. Then what does this do? It multiplies 4 by 3 and adds 1. 3 times 4 is 12, plus 1 is 13. So this box spits out the number 13 when you put 4 into it. Does that make sense? I hope it makes sense. Here, actually, ponder this for just a minute while I take a sip of water. Okay. Yes, there you go. Um, so f of 4 is the output, and f of 4 is equal to 13. 4 goes in, 4 gets effed up, and f of 4 is 13. That's what it is. Okay, now we're going to see a lot of different kinds of functions, and there are literally infinitely many types of functions. These are just basic examples, right? Here's another important one that we're going to see when we get to chapter 6, the sine function. And again, the letters are totally arbitrary. This doesn't need to be F. It doesn't need to even be G or H. It can be anything you want. The input variable doesn't need to be X. It doesn't need to be Y. It could be anything, T, Z, P. Again, smiley face, cat emoji. You can use the symbols are arbitrary. What's important is the relationship between the symbols. So here, it says SIN. That's the name of the box. That's the label on the outside of the box. It says, hey, this is the sine box. And when you put something into this box, it's going to do this. Take the sine of the angle given. So here, alpha is the input. G or sine says take the sine of the angle given, right? And then G of A or sine of A, because they're equal, that's the output. And so it's giving you the signed height of a right triangle with a hypotenuse of length 1 formed with an angle alpha. Now, that might be a little extra complicated. No worries. We're going to see that in chapter 6. We got time before we get to that, okay? But this is why it's important to get comfortable with this kind of notation. There's an input, there's a rule, and there's an output. All right? Input, function, output. Right. Now that we've talked about what a function is, gotten a little bit more intuition for what it is, there are some important sets associated with functions, in particular the domain, the range, and the codomain. Um, if you've learned this stuff before, you've probably heard about the domain and the range before, but you may not have heard of the codomain. And the codomain is also important, so I'd like to cover it in these classes. But let's go one by one. So given a function f, the domain of f is the set of all elements, the set of all inputs that work. In other words, these are the inputs that the function can actually process. The way you can think about this is not every function can work on every input, right? Wait, I use like, okay, think about a blender, for example, right? So if you have a blender, there are certain things you can put into the blender, and the blender will be able to blend them up, right? But there are some things you cannot put into a blender because if you try to, it will break the blender. So things in the domain of a blender are like fruits, ice cream, ice, yogurt, syrups, these types of things, right? Those are in the domain of the blender. The blender is the actual function. The blender is the box blending things up, right? So I can put fruits and all sorts of good stuff in there. It'll blend them up. And what comes out? A smoothie, hopefully a delicious smoothie. What is not in the domain of a blender? Well, this is basically answering the question, does it blend? Let's see, rocks are not in the domain. Metal screws, magnets, like there's a lot of things that don't blend, and those are not in the domain of a blender, right? So the domain is the set of all input elements that work, okay? Now, the range of a function is the set of all possible outputs. Okay, this is very different. This is the collection of anything that could come out. So you put some stuff into the blender, for example, what comes out? Smoothies. And there's a lot of smoothies, right? There's a lot of smoothies that can come out. Every single one of those smoothies is an element of the range, right? So the range is the set of all possible outputs. So from the domain to the range, that's why we have this picture right here at the very beginning. From the domain to the range. So for the blender example, the domain here is all the fruits and ice cream and yogurt and water and juices and things like that. This is the blending process, the blender itself. And then these are all the possible smoothies that can come out of that blending process. Okay, where was I? Right here. So that's the range. Now, we want to contrast that with another set called the codomain. And the codomain is the set or the space that contains the range. You can think of it as where the range lives. We're going to get some more intuition for that in just a second, but there's a difference between the range and the codomain. Um, for example, oh, here's a good example. A function may you put something into like the squaring function, right? Well, when you square a number, you get only positive results. So the range of x squared is all the positive numbers or the non-negative numbers, right? But the codomain is all real numbers. We're going to see this in action a few times, right? Okay. Um, Yes, yes, yes. Okay, so now let's talk about some representations of functions. There are four ways that you can represent any function. Verbally, using words, a description, multiply by three, then add one, verbally. You can describe a function numerically using a table of values. This is literally having a table that says says what goes in and what comes out. What goes in, what comes out, what goes in, what comes out, what goes in, what comes out. That's a way of describing it. Algebraically, this is probably what you're more comfortable with. This is when you have a formula. So if you've got a formula for the rule, we call that an algebraic representation. Um, for example, this one, there's an algebraic representation of the rule, right? Or I'm sorry, of the function. Multiply by three, add one. That's the verbal part. Okay, and then lastly, visually by a graph. And graphing functions is really, really helpful. We like pictures. Again, algebra and geometry are BFFAE. We're going to see lots of graphing functions in the next section. Okay, now I want to throw up this really fun example. Um, Here's an example of a function that is expressed verbally, and I want you to try to answer all of these questions. All right. So think about it. Oh, let me read the function out loud. Sorry. The function in this case says, take an arrow from the quiver and launch the arrow into the field with the bow. And I'm asking you, what is the function f? What is the input? What's the domain? What's the range? What's the codomain? All right. So think about it for a sec. Right. And now talk about it. If you're watching this with somebody, this is a great example to try to work out with your friend, with your peer, or you can just say something out loud to yourself. Then try to work it out on your own. All right. See if you can answer these questions, and then we will do it together. All right. Okay, let's do this one together. So, take an arrow from the quiver and launch the arrow into the field with the bow. What is the function f here? Well, in this case, the function f is the bow. The bow is the thing doing the launching. That's the process, right? So this is the bow. All right. What is the input? Well, the input is something that can be launched. So in this case, it's the arrow. Yes, I know there are other weird things you could try to launch with a bow, but it probably will not work very well. It's the arrow. What is the domain? So remember, the domain is the collection of all the inputs that work. So in our case, the domain is the quiver. It's the basket that's holding all the arrows. The collection of the arrows is the domain, right? And then what is the range? See, this is the interesting one. There's a difference between these two sets. There's a difference between these two sets. So let's see how this compares to what you answered. The range is, I'll just say, where the arrows land. And compare that to the codomain, which is the field, right? The field. So here's the thing. The location of the arrows where they land, that is the range. The codomain is the field, and the range lives inside the codomain, right? It's not that you're covering the entire field with arrows. Where the arrows land specifically, that's the range. We take an arrow out of the quiver, we put it into the bow, we launch it, that arrow lands somewhere, and where it lands, that's part of the range. The field covers where the range lives. That's the distinction there. There we go. So pretty close to what I have on these slides right here. All right. Let's look at another representation. So here is a couple of functions represented numerically as a table of values. Oops. as a table of values. Again, here's the input, here's the output, and then there's a corresponding point, or really I should say an ordered pair, like we talked about back in oh geez, section 1.5, I think. Anyway, input, output, and we can express that relationship as an ordered pair. This is another reason why algebra and geometry connect so well, ordered pair. Notice input here, output there, right? Input, output, ordered pair. Input, output, ordered pair. Here's another function. This function is called G. So input, output, ordered pair. Input, output, ordered pair. So that's another way of describing functions. Literally make a table of all the inputs and all the associated outputs, and that can describe a function. Um, Here is oh yeah, here's another example. Yeah, I wanted to show this because you'll see this on the homework as well. We can describe a function as a list of those ordered pairs. So this is actually the list right here. This is describing the function itself. See, the function f is this collection of ordered pairs, that. And then the function g is literally this set of ordered pairs. What is the domain of f? It's all the inputs. It's all the first entries. What is the range of f? It's the list of all the second entries. Oh, one thing I want to point out. Notice in this case, actually, I should let me use my pen for this one. Ding, 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 right? One thing I want to point out about this is notice here that there are some repeated outputs. In particular, we've got 9, 4, and 1 repeating. 9, 4, and 1. It's okay if an output of a function repeats. It just can't repeat from the same input. That's the catch. So here, -3 is getting mapped to 9, and +3 is getting mapped to 9. That is okay. That's not breaking the definition of a function because we're not putting in one thing and getting out two. We're putting in two separate things and getting out the same result. That is totally allowed. That's still a function, all right? And that's why the range is just the numbers 0, 1, 4, 9. That's all it is. You can do the same thing with G. I'll let you do that one on your own. Next, we can do it algebraically. So here is an algebraic representation of those functions before, or at least, well, includes those functions before, I'll say that. F of x is x squared. What is the domain of x squared? Well, what are all the inputs that work? Hmm. All of them. Every real number can be squared. So the domain is R, all real numbers. What is the range? Well, remember I was saying before, whenever you square a real number, you're always going to get something that is positive or zero, right? So no negative numbers come out of this function. No matter what you put in, you're never going to get out a negative. So the range is 0 to infinity. Same kind of thing for this. So here, this function g, this is the absolute value function that we studied back in chapter 1, right? What numbers can you put into the absolute value function? Any of them. Any real number you can take the absolute value of. What is the range? Well, remember, the absolute value is the distance from the origin, so it's always going to be positive or 0. So the range is this. The absolute value is never going to be a negative number. It's always going to be a positive number or 0. So the range is 0 to infinity once again. Right. And then here it is graphically. So this is a graph of these two functions. Y equals f of x, which is x squared. So what I'm doing is I'm plotting the x values on the x-axis, or the horizontal axis, I should say. And then I'm plotting the outputs on the vertical axis, which we call the y-axis a lot of times, right? And then if I use this function's continuous, I'm going to get a continuous unbroken parabola just like that, that actually goes on forever in either direction. I'm sorry, it goes on forever at the ends here. That's a visual depiction of this function right here, visual depiction of it. One distinction I want to point out here is this. The smooth curve here, that is f of x squared when the domain is all real numbers. These points are what you get when the domain is the integers. That's the integers, right? So that's the distinction between, for example, these. You might have noticed that this one was like squaring stuff, right? Well, this is a discrete point set. These are not filled in, right? These are discrete. -3, -2, -1, 0. It's not everything in between. So this is a discrete point set. And that's what you're witnessing here with these dots. Now, if you were to fill in between all those dots, if the domain is the real numbers, then you get the smooth curve. So not every function is a smooth, continuous curve. Functions can be point sets, all right? Same thing over here with the absolute value function. By the way, this is what the absolute value function looks like. It's an important one. We're going to see it a lot. So make sure you remember it. It's going to look like a V. This is one of the important graphs that you'll have to memorize in, I think, the next section. Excuse me. Yeah, but same idea. Inputs are plotted on the horizontal axis, outputs are plotted on the vertical axis, and then this is the set that shows the relationship between the inputs and the outputs. Right. So now that we've talked a bit about that, this is that same diagram or that same table that I had from section 1.6. We need to be able to talk about the domain and range and codomain easily, right? We don't want to have to write out a sentence every time we want to talk about these sets. So we have this really, really handy notation, interval notation, set builder notation, and then we have a visual interpretation of these sets, right? So this is just a refresher. We're going to use these a lot. You're going to get to play around with these a lot on the homework, but you want to get comfortable with this notation. Just a reminder, this is set builder notation. So remember, X is the symbol for the elements of the set. This line literally means such that. It's nothing more than that. That sounds weird. It literally means such that. And then here, X just has some property. However you want to describe the condition on these elements, you can write it right here. You can write a sentence. You can write an inequality. You can write anything, right? It just has to be some condition that you're placing on these elements. That's how set builder notation works. Now, this is where we're going to get led into a little bit of set theory. So remember, the domain of a function is the set of all the inputs that work or that don't break the function. Now, determining the domain of a function means we have to figure out all the things that will work. And the truth is that sometimes it's easier to look for what inputs work and determine the domain that way. Other times it's easier to look for the inputs that don't work and then just remove those from whatever the set, like the set of real numbers or something, right? So there's two ways to find the domain, and finding the domain, it's a bit of an organic process. You've got to kind of ask yourself, what is easiest? Is it easier to just figure out all the things that are gonna work? Or is it easier to look for the special cases that will break the function and cut those out and cut those out? So that's why we need to talk about a little bit of set theory. We need to focus on two set operations. One of them is called union, and the other one is called complement. Complement is like taking the opposite of a set in some sense. So let's talk about some set theory. The union. Um, for those of you that are going to take discrete math, you'll learn about these again, but you're going to go into way more depth. For our purposes, we just need the basics of these set operations. So let's let A and B be sets. Then the union of A and B is the set of all elements contained in A or B. We denote the union by this little cup symbol, by that little U. It's like a little cup. Oops, come on. There we go. And more specifically, we can say that the union of A and B is the set of all x's such that x is in A or x is in B. Maybe if you've worked with Venn diagrams in the past, this will look familiar. A lot of times in school, they'll use Venn diagrams. So let me do this. We could say it like this. Pretend this is the set A and this is the set B. then the union of A and B is all of that. All of that. All right. So the union is going to be everything in A or B. Everything in A or B. There we go. Everything in A or B. Actually, I probably should have used a different color. Here, one second. Pink. Maybe that's a little better. There we go. A or B. Just like so. So the union is everything. A little side note at the bottom here. When we talk about the union, we are not talking about the quote exclusive or. It is okay if an element is in both sets. So in particular, if an element is in here somewhere, that's okay. That's included in the union. We're not using an exclusive or where we are removing things that are in both. Okay. So union is just everything, everything. So here's one that I kind of want you to practice on your own, and we'll do it together. I've got some nice diagrams, but I want you to try to find the union of these two sets. A is the interval from negative infinity to 16 and exclusive, and B is the interval from 0 to 87, including 0. Okay? So think about it for a sec, right? Now say something out loud to yourself or to your friend or to your peer or to your dog about the union. Now try to work it out on your own, and we'll do it together in just a moment. Right, let's do it. Remember, the union of these two intervals is going to be everything that is in either or. I have the full calculation written out here. You don't need to go through all these calculations if you don't want to. If you can figure out what the union is just intuitively or visually, like we're going to see, great, go for it. You do not need to write down all these calculations. I just have them here for posterity and just for your own edification. So the union of A and B is the union of those two intervals. Which is the set of all x's such that x is in this interval or x is in that interval. Here I'm writing it as compound inequalities, and the x values that satisfy this inequality all satisfy this one, and this is the interval negative infinity to 80 to 87, excluding 87. That is the union. Let's look at a picture. I like to always visualize these things. Here I've drawn both of the sets and drawn the union. So here's the number 87, here's the number 16, here's the number 0. Down here you've got negative infinity, right? So the interval negative infinity to 16 is this one right here. And the interval 0 to 87 is that one right there. So what we're really looking for is the set or the interval that is the complete shadow of both of these. So it starts here and goes that way. We're taking all of it, right? No matter where the shadow lies, that's included in the union. So that's the union of these sets. All right, now we've talked about unions, let's talk about the complement of a set. So simply put, the complement of a set is the set of all elements that are not in the set. That's basically it. So if you've got a set A, the complement is the set of everything that is not in A, right? Not in A. We denote the complement by a little exponent, a little c. Let me zoom in. There you go. Right, A to the C. But sometimes if we know the quote universe where these sets live, sometimes we call it U, then we can write the complement as the universe set minus the set A. That's what that little slash means right there. It's called set minus. Basically, it means you take the universe and you cut out the set A. And when you do that, you're left with the complement of A, the complement of A in the universe U. More formally, we say that the complement of A is the set of all x's such that x is not in A, or we can write it like that. Oh yeah, this little symbol here, this little E just means in or is an element of. So if you ever see that, it means an element of. So here we're saying not an element of A. Right. Let's do an example. I wish, oof. Ah, I should put a pause here. Okay, pretend you can't see that. Pretend you can't see that. Maybe I can black it out or something. Okay, you can't see any of this. Hide this from your vision. Do not read this. I'll put a pause in the slides next time. Okay. Okay, you can't see that. My question is, try to find the complement of this set in R, meaning R is the universe. So if I give you this set, one, two, three, what is the complement of that set, right? So think about it for a second. Right now, maybe say something out loud about what you think the complement is. What is not in A, right? And now try to write it down. Write down the complement, and I recommend using, well, I recommend using set builder. I'm sorry, interval notation for this one. Okay, now let's do it together. Okay, let me erase this. Okay, now that we can see the answer, um, um, we're going to see what the complement is. So the thing to keep in mind here is that the set A is just the numbers one, two, and three. That's it. That is the set A. There's nothing else. It's not the stuff in between one and two. It's not the stuff in between two and three. It's literally like one, two, and three. Like it's just those three things. One, two, three. So if we take the complement of that set in the real numbers, it is literally everything except one, two, and three. So remember, complement here. Notice I'm saying X is in R. This is the universe, right? So X is not equal to one, two, or three. So it's going to be everything in between and outside of those numbers. Negative infinity to one, not including one, and then everything from one to two, not including one, not including two, everything from two to three, not including two, not including three, and then everything from three to infinity, not including three, not including infinity. Um, I think I forget where I said this before. Oh, I said this in chapter one. Just a quick reminder. Negative infinity and positive infinity, they are not real numbers. So they are never included when we talk about interval notation. At least for, well, eh, they're not real numbers. I'll just leave it at that. They're not real numbers. Okay. And since we are working in the real numbers, they are not included. I'll leave it at that. It doesn't mean that you can't work with them as if they were numbers, but then that gets into transfinite arithmetic and things like that. We won't be worrying about that in this class. Okay, let's look at a picture. Let's look at the picture here. So what is the complement of A? So I've got two images here. First, I've got the set A, right? So the universe here is the real line, all real numbers. The set A is just these 3 points, one, two, three. So if I take the complement of that set, it's everything except those. Literally, I'm cutting out the points one, two, and three and taking everything else. This is that. This is that. This is that. And this is that. That's the complement. Right. So this is why, or this is why it's good to know this stuff because, like I had mentioned before, let me go back a few slides to this one. Remember, sometimes when you're trying to find the domain or the range of a function, sometimes it's easier to search for what inputs work. Other times it's easier to search for what inputs don't work and then take the complement. So, like with rational functions, we may be like, oh, x cannot be equal to one, but everything else works. So the domain is going to be everything except one, right? Every real number, but not one. That's why you want to be comfortable with this notion of a complement and a union. Okay, let me go back to where we were. We were talking about this. Yeah, here we go. Now let's talk about the range a little bit. So remember that the range is the set of all possible outputs of a function. And the truth is that it can be difficult to compute without exploring the behavior of the function more closely. Um, this will take some getting used to, but domains are usually not that difficult to deduce. Ranges are usually not easy to figure out. So Don't feel weird if you're like, oh, I got the domain, that was easy. And then you go to try to do the range and you're like, I don't know how to do this. That's normal. That's normal. And you can think about it intuitively, right? When you make a box that does something, a lot of times you know what the box can handle. You know what you could put into the box. Now, as far as what could possibly come out of the box, that can be a lot harder to determine. You have to start looking at how the box works, what the box does to certain things, and you have to kind of figure out what's going to come out of the box, right? That's way harder than just saying, oh, I know this will work if I throw it in. That'll work if I throw it in. That won't work if I throw it in. That's why the domain is usually easier to figure out than the range. Now, some good practices for determining the range are these. Graph the function if it's possible to do so. Can't graph every function, but if you can graph the function, that's a great way to determine the range. Look for the minimum and the maximum values of the function, which we'll talk about in section 2.4, I think, or maybe 2.5. Then find where the function is increasing and where the function is decreasing. So these are good practices that can help you figure out the range. You'd be like, okay, are the values going up after this point? Are the values going down after this point? What's the maximum value? What's the minimum value? Is there a maximum value? Is there a minimum value? These can help you figure out the range. Now, in this course, I want to say this. In this course, for real, considering the graph is often the best method for determining the range. Um, we don't have enough analytical tools yet to easily determine the range of things. That's one of the reasons you take calculus, because when you get to calculus, you will learn techniques where you can analytically determine the range of a lot of functions as long as the function is differentiable, which you'll talk about next semester when you get into Calc 1. So what I'm saying is in this class, if you want to know the range, graph it, graph the function. And that's why we're going to talk about how to graph the function in the next section. We're going to talk about graphing all of these functions as the course goes on. But that's how we find the range in this course, graphing it. Okay. All right. I'm going to give you this example. If you want to try this one on your own, you can. So maybe I'll say this. I'll just go right to it. Find the domain and the range of this function, f of x equals the square root of 2 minus 6x. I'll give you a second to try if you want to try. Right. Okay. Now let's do this one together because we haven't seen a function like this yet, right? This is a square root function. You might remember these from the past, so I'm kind of building off of that, but we're only working with real numbers now. So for example, the square root of -1, which is I, it's undefined at this point. We don't know what that is yet. We don't know complex numbers yet. We are only working with real numbers. So in order for this function to actually be defined, we must have that the radicand, which is the stuff inside the radical, that has to be not negative, has to be positive or 0. So in particular, we need this. Okay, this right here, that is the condition on x that we need. We need 2 minus 6x to be greater than or equal to 0 in order for this function to work. If this is not true, then this function breaks, right? So now we're going to solve this inequality just like we learned in the last section. We're going to solve this inequality for x. So let's see. I'm going to subtract 2. Now I'm going to divide by -6. And remember, when you divide or multiply by a negative number, it switches the order relationship. So if I divide both sides by -6, I get x is less than or equal to 1/3. Boom. And that is the condition for our domain. That is the condition for our domain. So the domain is the set of all real numbers x such that x is less than or equal to 1/3. Here it is written in interval notation. Here it is written in set builder notation. There we go. So these are all the values that work. So if I set it another way, if you pick any number bigger than 1/3, that's going to break the function. So if you pick 1, like try to put the number 1 in as an input here. F of 1 is 2 minus 6 times 1, which is going to be -4. And the square root of -4 is not a real number. not a real number, not a real number. So doesn't work. That breaks the function. Now let's think about the range. So for the range, again, the best way to do it is to graph it. Um, Graph the function. You can use Desmos, you can use a graphing calculator. I recommend Desmos. And when you graph it, you'll see that it looks like this. And this quickly reveals that the range is all of the outputs f of x, such that f of x is greater than or equal to 0. In other words, the interval 0 to infinity, including 0. So this is what it looks like. Okay. And this literal graph here, it's the set of all points on the plane where y is equal to the output of the function. There you go. Yes. Oh, yeah. Desmos. We haven't learned how to graph these functions yet. We're actually going to learn that in the next section. But again, use Desmos. Graph these things in Desmos. Get comfortable with technology. Use the resources that we have available. All right. Um, Now, if you feel like a bad taste in your mouth about that, and you're like, well, am I going to have Desmos on the test? No, you will not have Desmos on the test. There are more analytical ways of doing it, but it's more complicated. So what we're going to rely on, for example, when you're taking the test, is you're going to memorize some graphs that we should know well, and we're going to look at transformations of those graphs. So that'll be the next section after 2.2. But if you wanted to have a more analytical way of determining the range, this is the answer to that. The smallest value of the square root function is 0. So this function here, the smallest it could possibly be, the output, the smallest the output could be is 0. So 0 is the minimum value. It's the lower bound of the range. Now, the function f increases as x gets larger in the negative direction. So if you keep plugging in negative x's that get larger and larger in size, these values keep increasing. And there's no upper bound. So you can keep making x large in the negative direction, and this will keep going up and up and up. So there's no upper bound to what this function can achieve. Um, so that right away means that our domain is, I'm sorry, yeah, that right away tells us that the range is 0 to infinity, right? Because x is also not restricted below. X can keep getting smaller, or sorry, x can keep getting larger and larger in the negative direction, right? So that means that f of x, the output, can keep getting larger in the positive direction. So this is like the analytical way of determining the range, right? As opposed to the graphical way. Okay, now let's put it all together. So here I have all of the sets plotted on the same diagram. I can zoom in a little bit, but not a ton because the way things are cut off here. So here is the function or the graph of the function. Here's the domain. Here's the range. And there you go. So now I have all the pieces here. The domain, negative infinity to 1/3. That's this right here. The range, 0 to infinity. And the way that I like to think about this, I can talk about this more in class. You can think about the domain when you have the graph as the shadow that's cast by the graph on the horizontal axis. That's the domain. So if you sketch the graph and imagine there was like a light up here, imagine there was like a spotlight, right? Right? Shining light. What shadow would it cast? And I think you'll see if you look at it, the shadow is going to be right here. And that's the domain. Now, if you want to know the range, you do the same thing, except now you put a light. Actually, I should have made this blue, huh? Can I change the color? Ah, never mind. Um, Now the range, you do the same thing, except now you put a light over here and you shine a light onto the graph and you see where the shadow casts on the vertical axis. And you'll see that it's actually going to be right here instead. In fact, maybe I should put this light over here just for clarity. Here's the light. Shine the light, and the shadow is going to be this shadow right here. That's the range. Okay. All right. On that note, let's play. That's it. So thank you again for watching. I'm excited to work with you in activity. Remember, you can always ask questions of your other instructors if you're taking it with someone else. Thanks again, and next time we will talk about the graph of a function. Have a good one, everybody.